So for those of you who are waiting very impatiently for quizzes and homeworks, the 2 quizzes are ready. The website was down. They'll be up so the 2 quizzes will be posted hopefully by today or this evening. And you'll have, as long as you like to complete them, but for those of you like myself who are supreme procrastinators, it's a very, very bad idea to postpone doing them, let's say to the end of the semester, because you'll have a lot more going on then, and none of the material will be fresh in your mind. So whenever I talk about procrastination, I think about alternate systems of education. So here's one example. If you study mathematics at Oxford or Cambridge in the UK as an undergrad degree, there are no exams for the 4 years that you study. That's not true. There are 2 exams. There's one exam that you take 2 years into it that counts for nothing. And then there's one exam after 4 years. And I'm not talking about one exam per subject. I'm talking about one exam for your entire mathematics degree. It's an oral exam, and it's an oral exam where the professors can ask you any topic that you've been studying for 4 years. Now, what a disastrous way of conducting things. I don't know. As I describe it, I feel shivers in my spine because I considered going there. Now, can you imagine what that would be like, how much pressure there would be? It takes a particular psychological constitution to get through that. But just quickly, there's an even worse system of study. At universities in Austria, here's how courses are structured. Pretty much like here. You take a course, and for each course there's going to be an exam, and the exam basically determines your grade. The only difference is that you can schedule the exam anytime you want. So basically, the lectures are like a resource for you to attend, and you can take the exam anytime you want. In fact, you can take the exam without having taken the course. It's just basically like an accreditation. Now, imagine how disastrous that is, because you have students who go through, and for 4 or 5 years, they don't pay much, but they pay, they study, they take courses, and they never feel that they're ready for the exams. They don't take any exams. There are students who have been there in college for 9 or 10 years and have never taken an exam. And then, stress builds and so, disastrous. Anyways. All right, so the quizzes, you can take them anytime you want. The quizzes should be very easy and, well, yes and no. So a word about the 2 quizzes. I think very, very easy. The first one is almost trivial. I give you a simple circuit with a few logic gates, and I give you something like a set of input probabilities. There won't be a single gate to look at, but a few gates. And you're asked to compute the probability at the output as a function of the probabilities at the inputs. I think for the non-electrical engineers in the audience, it won't be a problem because the only gates that I introduce are and or, I think. So this is just a check to see if the concept of logic gates operating on probabilities makes sense to you. So anyways, let me know if you have any issues with those 2 questions. Quiz 1 might take you on the order of 5 minutes. For quiz, that's quiz 1. For quiz 2, I give you a function. I can't remember what it is, but it's something like this. So I give you a function of t. G of t is some function of t. And what I want you to do is to step through the mathematics from last class. And all the slides are posted on the website, so you can just pull up the slides to remind yourself of how it's done, or I guess, since I didn't step through it myself, learn or how it's done. But the idea is these are coefficients. So it's 3/4, 1, 1/2 for this polynomial. And what I want you to do is convert this into a Bernstein polynomial. So for this, what you have to do is look up the slide where there's a formula from converting from a power form to Bernstein form. There's a formula for computing the coefficients of the Bernstein form from these coefficients. And then you have to elevate the Bernstein polynomial. By elevate it, again, in practical terms, what you have to do is you have to look up the slide where it tells you how to compute a new polynomial from a given polynomial that has higher degree. So compute the coefficients of a polynomial of degree 3, let's say, from a polynomial of degree 2. And you have to elevate it until all of the coefficients that you have are between 0 and 1. So no coefficients greater than 1, no negative coefficients. And then that's the answer that I want. It's the answer that I want because you could take those coefficients and you could plug them into the construct that I showed you, and then you would have a circuit that computes this function. So that's what I want you to do. So definitely quiz 2 might take you more than a few minutes because you have to look up the slides to figure out what's going on. Okay, any questions on that? I guess you won't know until you say, yes, what's your name? John.
Okay, so the quizzes are online.
Yeah.
Can we type into like type or something and put it up?
No, they're going to be Moodle based. So it's going to be a Moodle, the TA, he's struggling a bit to get this going, but they're going to be Moodle based in the sense it's a Moodle online quiz where you take it, you have to type in the values, and it should tell you if you got it correct. It should also tell you if you got it incorrect, but unlike other quizzes, it won't give you the answers because you're allowed to retake it. Yeah. But, and by the way, since it's in previous years, I always handled this on paper. And I was always embarrassed to handle this on paper because there's going to be something like 11 quizzes times 95 students. That's just a stack of 1,000 sheets of paper, each of which takes the TA perhaps a minute to grade, but that's 1,000 minutes. And even worse, even though it takes a minute to grade the quiz, it doesn't take a minute to enter 95 grades. So I thought this year we'll go to the online system. But I'd appreciate feedback, like honest feedback. If the quizzes are in any way confusing or if it's not working, just let me know. Okay. All right. So what I'd like to talk about today is going to be a continuation of computing with probabilities, but it's going to be some results that we've developed and published, but are definitely still in the research phase. So the presentation isn't very polished, and my explanation won't be very polished. So that can either go over well, because we can get discussion going, you'll find it can go over poorly, because it won't make sense. So the motivation, and this was the motivation that we had when we first started on this work, is to look for constructs, circuit constructs, that compute more than polynomials. Because all the examples we've seen are of the type where you put in some values. Inside of here, you have logic gates, proper circuit. I'm just trying to illustrate what's going on. Inside of here, you have logic gates. So inputs, logic gates, and an output. And if you have bit streams coming in, random bit streams of zeros and ones, each of which has a probability, then the output is a random bit stream, which has a probability. And that output bit stream is going to be a polynomial, in the sense that if the input consists of t, maybe multiple independent copies with probability t, then the output is going to be some function of t, which is going to be a polynomial, something like this, a polynomial in t, where again t is the probability value. Now, that's obviously a limited range of functions that we can compute for polynomials, but that's not because of our ignorance about how to structure the circuits inside of here. In fact, any circuit that just consists of logic gates will be a polynomial. I asked somebody about this a couple of lectures ago. Can someone repeat the argument? Why? Well, intuitively, if you feed in probabilities and all you do is you operate on it with logic, why will you get out a polynomial? So, Jason, any ideas?
I don't know, maybe the fact that when we did it before, we learned it as multiplication and addition.
Yeah, very, very good. So, but elaborate a little bit on that.
Well, the AND gates were multiplication or logical,
Yeah.
and the OR gates were logical.
Uh-huh. Okay, so suppose that the logic gates that we look at do operations like multiplication and addition. Then why will you expect that the output will be a polynomial?
Because polynomials are just
Yeah,
products and sums.
perfect. Sometimes I ask, when I press you, I'm pressing you to state the obvious because that's the answer that I want. But very well put, that I started off the sequence by trying to explain to you that an AND gate does multiplication. Let me write that down. I'll try to be more organized in the way that I write on the board. So an AND gate, which is a very basic logic gate, does multiplication. So if we have A and B as the probabilities of our bit stream, the output is going to be A and B. And then I showed you a construct that does scaled addition. That construct was based upon a multiplexer. I won't write that down now because I want to present this at a more fundamental level. So at a fundamental level, I'm sure some of you have seen this in your introduction to logic design courses. What are examples of universal gates? Gates from which you can compute any function, or equivalently, gates from which you can compute any other gate. NAND. So everybody knows that, everybody in electrical engineering, that NAND and NOR are universal. Okay, so here, let's suppose that we restrict as our fundamental set and instead not. So we'll take negation as our gate. So here if we have an input x, the output is going to be 1 minus x. So the not function does a 1 minus computation. So perhaps for the non-electrical engineers, since I haven't explained this might be confusing. So logically, what an inverter does, which is the symbol given here, and in circuit diagrams, sometimes it's just a bubble that's shown. The inverter takes whatever logical value you have and flips it. So if you have a 0, you get a 1. If you have a 1, you get a 0. So very, very basic. Seamus, right? Why does it perform a 1 minus operation in terms of bit streams?
Well, because
Yeah, perfect. So if the probability of getting a 1 here is, let's say, a quarter, then since this flips every 1 to a 0 and a 0 to a 1, it means that now at the output, the probability of getting a 0 is a quarter, so the probability of getting a 1 is 3/4. So 1 goes to 3/4, or 3/4 goes to 1/4, and so forth. So it's a 1 minus operation. All right. Now, a second ago, I asked the class, well, in terms of logic gates, what is a universal set of logic gates? And everybody immediately answered that the NAND gate is universal. So what is the NAND gate for the non-electrical engineers? It's just an AND gate followed by an inverter. So it's a gate, an AND gate with a bubble. So an AND gate with one of these guys stuck on the end, which is written just with this symbol. So this is a NAND gate. So the NAND gate, if in terms of inputs, what else can I use here? Let's use C and D. So Seamus, what is going to be the computation that a NAND gate performs in terms of probabilities?
it's going to be multiplication and 1 minus.
Yeah, so what would the formula be in terms of C and D?
So 1 minus C.
Perfect. 1 minus C times D. Okay, so this is multiplication, 1 minus, I don't know what to call this. Let's call this 1 minus multiplication. So just as a quick aside, and this is actually a topic that I've toyed with introducing in this class at some point. Discussing the theory. So all of you know that a NAND gate is universal. So for the non-computer engineers in the audience, the claim is that if the only logic gate that you're given is this one, a NAND gate, then you can compute everything with NAND gates that you could with any other type of logic gate. So any function that I give you that can be implemented with logic gates, you can change the circuit around and build the exact same function with NAND gates. You can also do the same with NOR gates. Let's not talk about that, but in a sense, ORs and AND gates are equivalent. I don't want to introduce too much logic design here. That said, for the next 5 minutes, I'm going to talk about this. So how do you guys know that NAND and NOR are universal? How did you? Because I'm guessing that you never had to prove that.
We just told Keeney had us for one of our assignments. We had to lay them all out. We
Yeah.
had to say, okay,
Sure.
implement this function with NAND gates.
So in other words, he had you perhaps consider all the different functions that you've heard of before, and show that you can build those with NAND gates, right? That's a proof that that all the types of gates that you've seen can be built with NAND gates. But it's not a proof that every function can be built with a NAND gate. Because, after all, the subset of functions that we've given names to is a very small subset. Now, this is, it's a fascinating topic. And it's a fascinating topic that definitely people like Larry Kinney, I'm sure he knew of this theory because he's an old guy. I'm saying this because the topic of what functions can be computed with what types of gates is a topic that isn't taught anymore in courses on logic design. Maybe it never was in undergraduate courses. But it's not even discussed in more advanced courses. And it's basically being forgotten by the current generation of digital designers. But there is a very rich theory. The theory is called the theory of ML post. Has anyone heard of the post lattice here? So look it up on Wikipedia if you're interested. It's called the post lattice. The post lattice is a beautiful construct that characterizes, in a much more rigorous sense, what types of gates can be computed from other gates. And it's much richer than simply saying that everything can be computed with a NAND gate. Because suppose that I was to give you a function like this. I'll use the electrical engineering jargon, but I'll explain what it is. A naught or B and C. So this is now a function of 3 variables. So for the non-electrical engineers in the audience, I wonder if I've used this symbolism yet. It's confusing because I'm talking, when it comes to stochastic logic, about arithmetic circuits where I use plus and minus in the regular sense. But computer engineers use plus to denote the OR operation. They use multiplication to denote the AND operation. And they use a bar to denote the NOT operation. So let me just write this as like this. OR, in parentheses, of not A, comma, and B, comma, C. So this function here, if you had to interpret it or write it down as a circuit, would be first you take the AND of B and C, then you take the NOT of A, and then you take the OR of the result. That's this. Okay. But suppose I was to give you a function like this. Is this universal or not? How do you decide? Can anyone say? John?
What do you mean by universal?
Can it compute every Boolean function, every function that can be completed with logic gates? You know that because I think you were told the NAND gate can.
Yes. Because it has both an and a not in it. You can just choose to use one or the other as you see fit.
So in other words, you could
Ignore the other inputs. Or wire them to zeros or ones.
So, but if you were to wire the A input to 0 or 1, okay, you could wire the A input to a 1 and then use the AND gate. So you're right. But let's say I was to give you a function. I haven't told you what exclusive OR is, but let's say I give you exclusive OR. Then it gets a bit harder, doesn't it? So this is a topic that maybe it could fall under the purview of the computation course, but I probably won't teach here because this course is intended to be multidisciplinary. But it's fascinating. The post lattice gives you a lattice of primitive functions, and it looks like a beautiful tree with a lot of functions that you wouldn't expect to be there, exclusive OR and exclusive NOR, what can be computed from those. And it fully characterizes not what is universal and what's not, but how you can decide whether, if I give you some small collection of gates, let's say I give you 4 or 5 big funky gates, whether or not you can compute everything. Or more specifically, it's called a lattice because presented in tree form, at the top is the everything function, and at the bottom is the nothing function. And every function that's in between, if you look what's above it, or if you look below it, it's what it can compute. So you go from the nothing to the everything with the expanding lattice, and it characterizes what can be computed with those gates below it. So, fascinating topic. The reason why this is near and dear to my heart is that there's a family connection here. So Emil Post did this work, if I'm not mistaken, in, I don't know, the early 1900s, something like 1910. So he did it long before digital circuitry was in existence, and long before the notion of a computer was in existence, but mathematicians back then were considering logic, and most of the theory of logic was actually developed long before computers were developed. But the family connection here is, so what Emil Post did is he showed the lattice, and he characterized it for all 0-1 functions, logical functions. He was interested in true and false. But what my father did for his PhD is he generalized this work, exactly the concept of the lattice, but he generalized it to functions that are discrete, so let's say map integers, but finite. So it would apply, for instance, to 3-valued logic, where instead of just true and false or 0 and 1, you have 0, 1, and 2, or maybe you have a set 0 through 7. And he characterized exactly, if you have functions of discrete variables, the complete lattice, the complete hierarchy of what can compute what. And it's really a profound mathematical result. And so I've always wanted to both understand and teach that, but I guess it's not within the purview of this course. All right, but I'm going somewhere with this discussion, because in the context of computing with probabilities, which is the topic that I want to teach here, we should at least consider the notion of what is a primitive set that we can use, or what is the primitive computation. And so borrowing the insight from the computer engineering world that the NAND gate is universal, or let's instead not explicitly consider the NAND gate, but let's consider AND gates and NOT gates. So increase our set to 2 gates. So now, and this is something that I guess would require proof, or maybe not, every function that we want to compute, in a sense, we have to compute it, or there has to be a way to compute it, by only performing multiplication and 1 minus operations. That is the full set of what can be computed. So in the green T-shirt, what's your name? It was Jacob. Okay, Jacob, Jason, and John. Okay. Are these all biblical names? Not quite. Jason isn't. It's just the common names are hard. All right. So Jacob. So what can be computed with multiplication and 1 minus operations? But can you say a little bit more about it, or what is your thought? It does seem constraining, doesn't it? That every operation that you want to do, you can only multiply things together and take a 1 minus.
You can approximate other functions as long as they're smooth.
Yeah, as long as they're smooth. Yeah. But stated differently, suppose that I give you a target function, like a polynomial. How would you, with this insight, how would you go about constructing the circuit? I showed you one way of doing it last time. That was a specific way. But the operation of multiplication and 1 minus, this seems like a different topic, right? Okay, I was going to start with sequential constructs, but since I've talked about this, let me go right to this topic. I'm glad, and so this is my future house, but this is a drawing, and I'm very proud of this drawing. So this is with the modern rendering software. That's all just a drawing. Pardon me? So I'm going somewhere. We're going to be talking about multiplication and 1 minus operations and what to do with multiplication and 1 minus operations. So the specific problem that I'm going to pose is, suppose that we have a circuit that computes constant probabilities. Well, actually, that's not going to be the case. But suppose that we have a means of generating constant probabilities. So we have a means of generating, let's say, 0.4 and 0.5 coming in. What does that mean? I hope everybody's on the same page here. It means we've got bit streams flowing in here, where the probability of a 1 in this bit stream is 0.4. The probability of 1 in this bit stream is 0.5. But suppose what we want out is 0.757. So what we want is a circuit that transforms probabilities into probabilities. Why would we want that? Any ideas, Jacob? Just based upon what we saw in last lecture?
Just computing functions and variables.
Yeah, well, if you think the constructs that I showed in last lecture, recall that we had, for instance, the big multiplexer, and we have coefficients going in. The coefficients being bit streams that I want to fix at constant values to compute a function. So suppose that for one of the coefficients in that Bernstein construct, was supposed to be 0.757. How do we get that? That's going to be the theme here. So any ideas? How do we get something like 0.757? Never mind the 0.4 and 0.5, but how might we get it? I guess I haven't really talked about that, meaning I just assume that you have bit streams fixed at whatever probability you need, but how can you get that? So sitting next to Chris, what's your name? With the glasses off so you can't see me pointing at you?
I know you're pointing at
Okay.
Alex.
Alex, that's right.
Well, what are we starting with? Do we know what we're starting with?
You're starting, you're the only constraint is you're not allowed to invoke magic. So you're not allowed to say, by magic, we have something. Because that's never helpful in engineering.
Okay. So I'm looking at your slide here. I don't know if I'm topping out on creativity here, but you've got a random source and a constant value and a comparator. So we could set the constant value to be something relative to the random source so that if we compare the constant source to the random value, we will take whichever one is more or less, and depending upon what the value of the random is, like say we choose less, and the constant value is set to be 0.4, you will only get values from the range of 0 to 0.4.
Okay, that's really good.
And you will take an average of whatever probability, or an expected value of whatever you get from those probabilities, and you will have your probabilistic output.
Okay, I think that's exactly right. Let me restate that. So the simple answer, which I was expecting people to offer, is for the computer engineers, you might have shouted out, just use an LFSR. So Hassan, what's an LFSR?
It's a linear feedback shift register and consists of some XOR gates and some flip-flop that can generate a new pseudo-random number.
Perfect.
It's like
Okay, so again, not within the purview of this course to discuss, but there are standard ways with logic gates and with registers, these are devices that hold binary values, to generate sequences of binary numbers that are in fact not random at all. They're the opposite of random. They're deterministic, but they look random. So the sequence that you get has this roughly the same statistical properties as a random sequence. And that's, in fact, how in all the work that we've done, nearly all the work, how we generate our random values. So if we need 0.757, we'll start by generating a random sequence with something like an LFSR. So I won't talk about that, but just assume that something like the LFSR, we'll call it our random source. And in fact, for this sequence of slides, I'm more ambitious because it turns out that using this technique that Hassan described is kind of expensive. We need a lot of gates just to generate our random values. And what I'm hoping for is that we can use some sort of physical source of randomness, something like thermal noise in the circuitry. And there are different ways that you can tap into the thermal noise of silicon to get, let's say, voltage measurements that are related to temperature variations in your circuit that are pretty random, or pretty random, that look pretty random. So assume that we have some source of randomness that gives us a Gaussian distribution as shown up there. The point is that if you're using something like thermal noise, you're not going to be able to find thermal noise that has exactly this coefficient of randomness for its probability. Most likely, the source of random noise you're going to have is going to be fixed. It's going to be whatever it is. The same thing with an LFSR, the computer engineering way of doing it. You get a sequence of bits that looks random and has this random statistical properties, but there the probability of 1 versus a 0 is a half. So you start off with something that's a half. So the question is, let's say you're given some source that gives you a probability of 1 versus a 0 that's a half with that kind of Gaussian distribution on whether it's a half or not. Or what, rather, the value that you get will have this sort of Gaussian distribution. how do you transform it into some value like 0.757? And I think, Alex, this is exactly what you described. What you do is you can take the value that you want, like 757, load it into this box, then have a comparator. And I hope this is making sense for the non-computer engineers because these are just operations. So we just take the random value and we compare it to 0.757. If the random value is less than 0.757, we generate a 0. If it's greater than 0.757, we generate a 1. So Alex, why does this give us what we want? Is it obvious?
So at a certain percentage of the time, so since this function is a less than function,
yeah.
you have R here. And there's a certain percentage that it's going to be less than C.
Uh-huh.
You're showing there an integration over your probability density function. So if you pick a certain constant value, say 0.6, if you integrate everything from 0 to 0.6, that's the probability you're going to get a 1 from this comparator.
Perfect.
Then otherwise you're going to get a 0.
Perfect.
But
that's good. That's exactly what I was looking for. For the Unite students, to summarize, this is the definition of probability density function for a random variable. If we pick a given point along the x-axis, a given value, then the probability of obtaining a value less than the one that we've chosen will be the integral underneath the curve of the PDF. But all of this, I think, is very intuitive. So we simply generate something that has a random value of, let's say, a half. We compare it to a constant value that we want, and the result is a bit stream, ones and zeros, that has the probability of a 1 versus a 0 being whatever we set to the constant value. So this is a nice, clean construct, and potentially a very good way to generate our bit streams if we have access to some source of randomness. And so, again, sometimes when I make the pitch for this entire idea to the right audience, people get very excited because there are circuit designers who spend a lot of their time battling randomness in their circuit design. You've got things like process variations and so forth. When electronic circuits are built these days, because the feature sizes are so small, actually from circuit to circuit, the exact behavior will not be the same. Circuits can't be built exactly the same in terms of the thickness of the different atomic layers. And then as the circuits operate, as they get hotter and cooler, there are variations that happen within the circuit. And the circuit designers, the variations in like the voltage or of the power supply for the circuitry, they spend all their time battling the randomness because they want their circuits to compute correctly. In essence, what we have here is a paradigm where randomness is our friend. We want randomness. And that's a profound difference. We're seeking to design circuits where the randomness that occurs here is our friend. We want things to be as random as possible to get good bit streams. Okay. But the topic that I'll discuss for the next few minutes is this topic of and 1 minus here. So here, this will be a bit of a discussion on the cost of building the circuitry. But the argument that I'll make, and you can accept it or challenge it, is that generating the numbers, the random source, is expensive. Generating the numbers using a standard engineering construct is expensive. You need a bunch of gates. If instead you can exploit something like thermal noise, that's potentially very cheap. But now if we look at the paradigm that we've suggested, suppose we use random sources like thermal noise. Those are potentially very cheap. We can get a whole bunch of randomness for very little. But then compared to that, setting a constant value may be expensive. Because if you think of it, I just said, well, let's generate a constant value of 757 that we'll use in the comparison. But setting this particular value will require either circuitry or will require electronics to do. That can be expensive. And so the argument here is that you may have lots of sources of randomness that are cheap, and you can use as many of those as you want, but it's expensive to pin down specific values. And if you want to pin down a lot of specific values, then your circuit is going to get quite expensive. And if you think of the construct that I talked about last time, the Bernstein polynomials, to implement a function, you need, let's say, a whole bunch of coefficients. Those coefficients are constant values. If it's expensive to generate all of those, then you might be losing out. So can anyone see where I'm going with this, Alex? Sorry. So I've received feedback from some students that they really dislike it when I go back to the same student every time. So I should have some kind of code where you hold up like a red card that says, like in an auction, I'm done. But maybe just grimace.
It's not that. I just don't know how you want me to answer this.
I know.
Because I just look at the slide and I guess where you're going with it.
So, but this is, but that's
I'm kind of metagaming the class here.
But this is, it's a particular teaching style. And it stems from when I was in grad school, I had a professor who taught algorithms. And it was the most amazing class I ever took, because we'd come to class, and sometimes I'd be tired, sometimes I'd be cranky, and he wouldn't let us just lean back and listen. He just constantly, and it wasn't so much that he forced us to interact, but he would never just tell us the way it was. He would always set it up so that there was like a puzzle that we had to solve. And it was just very rewarding. Even though I was tired, I didn't always want to do it. I came out of that class feeling that I'd gotten something from the lecture. So whether I'm successful or not, that's what I'm trying to do here. But that means I'm constantly asking you to predict exactly what I'm going to say, which can be annoying. So here, where I'm going with this is that if we need many different probabilities, like we need all of these probabilistic values as our coefficients, but it's expensive to generate them, perhaps an alternative is to not generate all of the random values that we need separately, but instead just generate a few, maybe just generate a half. And then do what? Well, that's what this box suggests. Look at ways of building a circuit that can take a limited set of probabilities that we generate, and through logic, so through logic circuits, not through random number generation, transform those values into the ones that we need. So
I was kind of expecting you to say we were going to have, say, one constant value, and then we'd use our random source to get one kind of probabilistic function from this comparator.
yeah,
And then we'd feed it with the random source over and over again and try to get different.
that's interesting.
values up and down.
That's interesting. So, but feed it back, so like tinker with the random source.
Well,
Yeah.
you'd have the random source at one constant value into here, and then you would take the output
Yeah.
of this random source as the next constant value or the random source.
That's interesting.
But that's not where you're going with this.
It's not, but it's interesting. Because then, yeah,
Because then your constant sounds constant.
not so constant. Well, then you might get interesting behavior. Interesting. So here, the idea is that we have cheap and we have expensive. So let's use lots of cheap, and let's use very little expensive. So let's have lots of random sources. Let's have a single constant value. So generating the constant value, we can generate it once and just store it somewhere. Yes, John?
I have a question on this black box
Yeah.
manual that you described. Those aren't probabilistic streams coming in, right?
They are.
Analog levels?
No, these are, so this is already, so where I'm going with this is we generate probabilistic bit streams, like 0.4 and 0.5. We generate them like this. And then now we have ones and zeros flowing into circuit. Inside of here, I want to put, let's say, an AND gate. So let's say I put an AND gate. 0.4 times 0.5 is what? Well, it's going to be 0.2. So I've transformed it. And if I take an AND gate, then it's going to be 1 minus 0.2, which is 0.8. So obviously I'm able to do stuff. But the question is, how do I do stuff with a specific target in mind? That's where I'm going. Yeah.
I just didn't know if there's analog.
I know it's a bit confusing here because I am kind of glossing over the fact that here the comparator, as I suggested, I'm doing that comparison, that constant value, as an analog comparison in the generation. So this is where I'm generating the bit streams. I'm intentionally not trying, I'm trying to avoid circuit level discussions here. But thanks. Okay, so this is going to be the strategy. Use as few constant values as possible, because they're expensive. Use random sources, generate a whole bunch of bit streams. So our currency then, which is cheap, is going to be a whole bunch of random bit streams flowing in, which are all independent, and they're good quality bit streams, but they have, let's say, a fixed probability, or we might have a few fixed probabilities. What do we do with that? So the challenge then is going to be how to generate many different probabilities from a few sources. I guess I'm over-explaining it here. But is everybody following the premise? Okay. So in the spirit of prompting you guys, let's in a few slides, I'll look specifically at 0.4 and 0.5. What can we do with 0.4 and 0.5? So Jacob, any ideas? How can we generate 0.757 from 0.4 and 0.5?
Multiply them to get them smaller, and then do 1 minus to get them
Bigger? Yeah, but just keep doing that until you hope you get the right answer. That's actually, a lot of science is done that way. Can you begin to think of an algorithm for doing it?
It would take a bit more than just what I would be able to think of right now.
Yeah, but it's now, I hope, an interesting puzzle. The puzzle is, and I think that this is actually more fundamental than I'm positioning it. So if we're dealing with logic gates as our fundamental construct, then in conventional computer engineering, a NAND gate or an AND and NOT gate is our primitive set. And everything that we want to do, we can do it with OR gates and exclusive OR gates, but the OR gates and exclusive OR gates can be built from AND gates and NOT gates. So any large function that we want to compute, we have to be able to reduce it to a sequence of computations with just AND and NOT. In the probabilistic sense, we have to reduce every large computation that we want to do to a multiplication and a 1 minus operation. And somehow I feel that, I don't know if I can articulate this well, but if you actually look at what's happening at a circuit level, so at the level of CMOS, which is the circuit level for the computer engineers, the operations that you can do really boil down to multiplication, which is to take a fraction of a fraction. So you have, let's say, a half going in. You can multiply it by a quarter. So you can take a quarter of a half. That's what you can do, with the set of CMOS transistors stacked together to give you an AND operation. Or what you can do is you can flip it. You can take 1 minus. And in a real sense, all of our modern civilization, which is built on transistors, I don't know if this is quite right, but I feel that it's the beginnings of a theory of, not in terms of the digital values, but in a more abstract sense of the type of computation that we're performing. What are the fundamental operations that circuitry can do? And maybe a good candidate is it can do multiplication and 1 minus. And everything else that we conceive of has to be done in terms of multiplication and 1 minus. Okay. All right, while I was rambling, does anyone have ideas? I'll step through some examples. Okay. I think there's a few slides here that I often do this. I spend way too much time to set up the problem. So the problem here is, suppose we've got random bit generators that can give us some set of probabilities, like P1, P2. They can give us multiple copies of P1 and P2. So several P1s, several P2s, several copies of P2, perhaps as many as we need. But what we want is some other set, like maybe Q1, Q2, Q3, and Q4. So we want different probabilities. How can we design the circuitry inside of here to transform the given probabilities into the desired probabilities? So, and from a theoretical question is, what is the smallest set S? So can we generate any probability value that we want? You pick the value Q1, Q2, and Q3. Can we get it from a single probability? Do we need 2 probabilities? Any guesses?
I think we can generate any probability from 2 probabilities.
From 2? What about from 1? So, yeah. What's your name? Rishabh. With an R, right? Yeah. Rishabh. Okay. I think I got that. So the answer is, I don't know. That's true for a lot of big questions that any professor poses. But with students, we came up with some answers. So it turns out 0.4 and 0.5 are universal. We can prove that you can generate any probability value you want, any decimal probability you want from 0.4 and 0.5. And that's kind of interesting, that 0.4 and 0.5 are somehow an easy universal set. We came up with a single probability value from which you can generate all the others. So why don't I just tell you that probability number? Because so that probability value is something like 0.1257, but it turns out to be an irrational number. So it's not even a number that I can express as a fraction. So 0.4 and 0.5 are nice, easy, simple, rational numbers that work. And we know of an irrational number that works, but we don't know of anything else in between. But this is definitely an open question. So we haven't proved that there is no, maybe 0.3 works, as a universal probability. We just don't know. So again, now I'm overstating what to do, but suppose we want 0.6. So someone tell us this will be more fun. So John, how do we get 0.6? Not of 0.4. So 0.4 knotted gives us 0.6. How do we get 0.2? I think I told you guys that. You just multiply 0.4 and 0.5. So if we start with 0.4 and 0.5, we can do 0.6 and 0.2. How can we do an arbitrary? This is where I was just stating that we found sets of 2, 0.4 and 0.5, and we found a set for 1. So in terms of the discussion of 2, I won't step through the details of the proof of the algorithm. I'm simply going to give you guys a few examples and leave it at there. But this will be one of the topics that you'll have to play around with yourself on the homework. I'm going to give you some value like 0.757, and I'm going to ask you to build it with just multiplication 1 minus operations. And it's an interesting problem, isn't it? How do you start with 0.4 and 0.5 and get 0.757 with only multiply and 1 minus operations? So what's an example? Here's 0.757, and here's the sequence. So we start off with 0.4, and it turns out the way we know how to do this is in a linear sequence. So linear meaning we just, on the same value, continue to operate. That actually doesn't give us a very good circuit, if you think about it, because it's a circuit that's a long sequence. So in practice, what we do is we generate the long sequence. And once we have the long sequence, which is a regular circuit, we take that circuit and we throw it into our logic synthesis tools, which then make an efficient circuit out of it. But the sequence here, to just read through it, is 0.4, 1 minus gives us 0.6. Times 0.5 gives us 0.3, 1 minus gives us 0.7, and so forth, all the way till we get 0.757. So that's the algorithm. That's an example of it. It's not the algorithm. I'm not going to tell you what the algorithm is because it's kind of complicated to state. And that's specifically what I want you to play around with on the homework. And to be honest, I suggest that you can read the paper, which is posted on the website, that gives you the algorithm. But it might be more fun to play around with it yourself. And it's totally, for all the examples that I give you to do on the homework, it's totally feasible to play around with it yourself. And maybe after playing around with it yourself, then you can go and look at what the algorithm is. And my hope is that perhaps you'll appreciate the algorithm, or you'll have even better ideas of how to do it if you first look at it yourself. If I step through the algorithm, it's basically an inductive algorithm where it's inductive in the sense that for every, by the way, all of this is predicated on the assumption that we're working in base 10 with our probabilities. So we're working in base 10, which means that the numbers that we have as our targets, or our range of targets, are written in decimal. Why does that matter? Can someone say? So Mackenzie, why does stating a probability in decimal versus hex or binary, why could it make a fundamental difference here? Go ahead.
In a different base, it might repeat.
Yeah, exactly. So if you guys in undergrad courses have ever been forced to convert between different bases, like if you convert between decimal and binary, you can often have a case where a decimal is repeating in one base, but not in the other, or vice versa. And so here, the name of the game is precision, and the claim is that we can implement any decimal probability, so any probability that has a finite number of decimal digits using this procedure. But if we went to a different base, then we might have an infinite repeating decimal, and hence we wouldn't be able to implement it exactly. So all of this is predicated on us beginning with and targeting decimal probabilities. So the algorithm starts by, and this is an easy exercise for you to do. In fact, this would be a good exercise for quiz 3, even though maybe we're getting ahead of ourselves, is start with just a single digit and figure out how, based upon 0.4 and 0.5, you can implement all of these. And we've already done quite a few, haven't we? Well, 0.4 and 0.5 are given. We did 0.6 and we did 0.2. All you need is to generate the others, to figure out what simple sequence of operations you need to generate the others. Then, as it turns out, the algorithm is inductive in the sense that it goes, if we wanted to implement 0.757, we would first figure out how to do 0.7. Then, based upon having done 0.7, we would figure out how to do the next 5 and the 7. We can't do the digits separately, so it's not as easy as just doing 0.7 and then doing 0.5 and then doing 0.7. But that's how it builds. And there's basically just a finite set of rules for every number that you encounter based upon the previous number that you've encountered how to do it. But I want you guys to play around with it. Okay. Any questions on this, on what you'll have to do for the homework, or why this was interesting or not? So here's what the circuit would look like. Here in this representation, and is multiplication, and the dot is the 1 minus. It's just the easy way to express it. Okay. So let me switch topics in the remaining time. And so this will be the last topic that I'll discuss in the context of probabilistic circuits, or computing with probabilities. Well, actually, there was one other topic I wanted to do. Okay, let's go back to that one. So, after having argued and perhaps even convinced you that the only types of functions that we can implement with stochastic logic here is the jargon for, it's not even a good term, I don't like it, but the term for logic, so logic gates, that operates on probabilistic bit streams. So after having tried to convince you that the only types of functions that we can implement with a stochastic logic are multiplication and 1 minus, and by extension of that, if you just look at what can we do with multiplication and 1 minus operations, well, if we do something like this times c, if we nest multiplication and 1 minus operations, and that's what any circuit will be. It will just be a nesting of multiplication and 1 minus operations if all we have are and not gates. If you think about it for a moment, when you multiply this out, you get a polynomial. Is that clear, Jacob? So why would you get a polynomial if you multiply this out?
Because any composition that polynomials is polynomial.
Yeah, very good. So what we have is a polynomial. Multiplication or multiplication 1 minus is a polynomial. And any composition of polynomials, meaning if you stick polynomials inside the variables of polynomials, you just get polynomials. Okay, so after having convinced you of that, now I'm going to show you how we can, in fact, get non-polynomial functions. How? There's this, I won't go there. But breaking the rules, we're going to break the rules, but it's still going to be a digital circuit, but I'm kind of prodding all of you to anticipate how. So Michelle, any ideas? How can we break the rules and get, so here, this is the function that's called tanh, hyperbolic tangent. That's what mathematicians call it. But this is a very useful function from an electrical standpoint. It's basically a hard thresholding function. So if the input is less than 0, the output is here. I've scaled the axis here. So let's pretend that that's 0, and that's 1, and that's 0, and that's 1, instead of -1 to 1. So if you're less than 0.5, then the output is 0. If you're greater than 0.5, the output is 1. So it's a hard threshold. So why is that a useful circuit or a useful construct?
Is it like a comparator?
It's exactly like a comparator. But if you think about it, if you're a digital circuit designer at the circuit level, what you want is you want a circuit that outputs a 0 or 1. You don't want a circuit that outputs 0.8 volts. And so having this kind of, it's a nonlinear function, this kind of hard nonlinearity is exactly what you need to implement digital circuit, digital computation. But it's definitely a non-polynomial function. There's no way that you can exactly compute tan h with a polynomial. So any ideas how I'm going to do this? Yes, John.
My only ideas are some sort of transform where you have coefficients of that transform and you bring it back.
Yeah, that's very good. So the way that I'm going to cheat or bend the rules is we're going to have a circuit that is sequential, a circuit that has feedback. So all of the constructs we've shown and the entire mentality has been we're going to have a bunch of gates. Those gates will feed forward to produce the output. But in computer engineering, things get interesting when you have a circuit where you take the output and you feed it back to the input. Then suddenly things get much more interesting or much richer. Yes, what's your name?
Manga.
With an M? Manga?
Manga.
Manga.
So can we not do Taylor series expansion?
We could. So a Taylor series expansion of tan h is definitely an option, where we could express tan h, or this function, as a polynomial or Taylor series expansion. But we require a lot of gates, even within the stochastic paradigm, because I don't know, the function for it, I think, is shown here. So the function, this is the function for tan h. And we should plug this into MATLAB or Mathematica and see what the Taylor series expansion of this. To get an accurate Taylor series expansion, it might be a lot of terms. Yeah. But as it turns out, if we modify the rules, I shouldn't say break the rules, to extend the type of computation we're doing to computation in which there is feedback, then suddenly we can compute a function like this. Let me explain to you how we compute this function, because it's easy enough. But I'm not oblivious to the fact here that now suddenly I'm assuming a lot of knowledge of computer engineering. So just let me explain it as best I can, but ask questions. So to do this, what we're going to use is what's called a finite state machine. The finite state machine, this is horrible jargon. I don't know why it's a machine suddenly. So if you listen to commercials for a BMW car, it's a car. And they call it the ultimate driving machine. So somehow calling it something other than what it is makes it seem more important.
Technically, a car is a machine.
I know, but so is a lawnmower, and it's not the ultimate driving lawnmower. It's a car. It's better to be specific. So the finite state machine is nothing more than ordinary logic gates with an element that holds what it computes. So holds the results of the computation and then feeds it back in. So I won't explain any of that. Instead, we'll jump right into the state description of what's going on. And I apologize, these slides are simply not refined. There's nothing wrong with what's on there, but this, if someone walks in, is an ugly slide. It's ugly in the sense there's not a single word of text except for sequential. So let me get rid of, first of all, the tan h. There, that looks better. So let's begin our discussion here with, I'm just going to write down some bubbles. Those bubbles are going to be states. So here's a state, here's a state, state, here's a 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 state. Am I at 8 yet?
Yeah, you're at 8.
Okay. So each state is going to be a state in which the circuit can be in. That's all we have to know. But let me at least draw the box of what's going on. The box is going to be a very simple box. What goes in is a bit stream X. So a bit stream, random bit stream, nothing more. what comes out is going to be a bit stream Y. So bit stream in, bit stream out. In terms of the input-output specification, it's pretty simple. And my claim is that this particular circuit, the bit stream out will be Y along the Y-axis, and the bit stream, given a bit stream X along the X-axis, again, pretend that it's between 0 and 1 and 0 and 1. And to do that, we're going to build a circuit that maintains a state. And I won't, for the non-computer engineers, go into the details of how it maintains a state. But a state meaning it can remember, just think of it in terms of these being positions. So imagine here I had 8 positions, 8 squares on the floor. And the machine, which is going to be me, can stand in one of the squares, or it can move to the next square, or it can move to the next square, or it can move back. That's what the circuit can do. And what I'll describe is simply when the machine chooses to move from one square to another square. So it'll choose to move from a given, I should say circle instead of square. It chooses to move from this circle to this circle if the input that it receives, which is X, is equal to 1. So it goes to the right whenever the bit is 1. It'll go to the left whenever the bit is 0. And then when it reaches the end, well, it's got nowhere to go. So here, if X equals 0, it stays put. And over here, if X equals 1, it stays put. OK, is it clear? I haven't filled in all the arrows, but is it clear what's going on? And it's just bitstream X comes in. If we're in a given state like this one, we go to the right if we get a 1. If we get a 0, we go to the left. But of course, if we're all the way at the left and we keep getting zeros, well, we got nowhere to go. All right, so now can anyone guess? So Jacob, can you guess? How are we going to implement this wonderfully complex function, tanh, with this finite state machine? And what we have to do here is to specify for each state that we have what the output should be. So we're simply going to assign, we're going to say, if we happen to be in this state, then output a 0. If we happen to be in this state, output a 1, for instance. So all we have to do here to complete the description of the finite state machine is assign zeros or ones to each state. And the claim is that there's a way to do this such that we get tanh. Yeah, Tor?
You can just make the right side have output of 1 and then the left side output of 0.
Perfect. So what's the reasoning here? Talk us through this. So suppose that here, for this state, so let's number these states. Let's call these 0, 1, 2. We should use different color markers. So go for it, Tor. Explain.
So if you let it run for long enough, it's going to, if the probability is greater than 0.5, it will tend towards the right side, and it will eventually get into the state 7 and continue to output 1, whereas if it's below 0.5, it will tend towards the left side.
Yeah, very good. So think about this for a moment. Suppose that we start in state 3. It doesn't really matter what state we start in. So we start in state 3. And suppose that the inputs that we're getting, I really wish I could just scribble on the screen, but people might get angry if I just cross these out. I want that to be 0, and I want that to be 1. So imagine that we're here, which is, in fact, 3/4 as the input. 3/4 is the input, which means that among the inputs that we're getting, the zeros and ones, we have a lot more ones than zeros that we're getting. So if we have a lot more ones than zeros that we're getting, it means that even though we'll occasionally get a 0, about 1/4 of the time, we're going to quite quickly bounce to the right, won't we? Because we keep getting 1s. We may get a 0, we may get back. And once we've bounced along far enough, let's say we're stuck all the way here, it really doesn't matter if we occasionally get a 0, then we'll go back, but then we're still getting more 1s than zeros, so we'll continually get pushed to this side. So this means that the output, if we have slightly more 1s than zeros, so if we're at 3/4, 3/4 is the input here, well, then we're pretty much going to be getting 1 as the output. And similarly, if we're considerably less than 1/2, so if we're at 1/4, we're going to be getting zeros as the output. So it's only when we're at nearly at 0.5, so when the number of 1s and 0s is nearly equal, then we'll be getting both 1s and 0s at the output. And if you think about it for a moment, the more states that we have in the sequence, so instead of 8, if we had, let's say, 32 states, then it means that the width of this transition period will get narrower and narrower. Why? Manga, right? Yeah.
Yeah, because if you have more number of states, the probability of going to the right or to the left will depend. You will keep on oscillating somewhere in between. If you have a probability of half, you will oscillate between the half of this one.
Uh-huh.
So if you have more number of states, so it's more likely that you'll be well down into the sequence.
Perfect. So if you have more states, and if you have slightly more 1s and 0s, it means you can travel further to the right. And the further you travel to the right, the less likely that you are to accidentally bounce back to the left. And so, and it turns out that you don't have to increase the number of states by very much to shrink this transition period more and more and more. So that's the construct. Of course, it should properly be justified in terms of a proof of why it behaves this way. And we've done that in a sequence of papers. But it's really intriguing. Here's why it's really intriguing. So let me just try to explain. I can also step forward and show you guys more constructs with it. But instead, let me explain to you why I think this is intriguing. And it's intriguing in the sense that this is an area of active research that we're working on. So before showing you this finite state machine implementation, all the functions that we had were just polynomials. That's all we could compute. And they were simply functions where we would take an input x and compute an output f of x that just depends upon the current x. That's all we were able to do. Now, in terms of building a computer system, that's an important step because this is, in a sense, the most important task of the computer system that given, let's say, an input x to compute f of x, or to given two inputs x and y, compute f of x and y. For instance, your computer system in a given step might have to do addition. It might have to do multiplication. So your computer spends most of its time, in a sense, doing that operation. But that's not a computer system. A computer system is one in which you can give it a sequence of instructions, and it'll step through those sequence of instructions. And for each instruction, do a computation like x goes to f of x. And so this entire paradigm of bit streams flowing in and bit streams flowing out, even though we were able to argue that we can implement really complicated functions, like the gamma correction function, t to the power 0.5, with magically few gates, it didn't have much traction because the circuit that does gamma correction, which may be part of a video card that you have in your computer system, well, it's just one part. And the rest of the computer system operates in binary, in a positional system. And so you somehow have to take your positional binary values, convert them to bit streams, take those bit streams, pump it through the stochastic circuit, and then take the outputs. But it meant that, this isn't an idea that works very well as a plug-and-play idea. It doesn't work well as a plug-and-play idea because it's expensive to generate those stochastic bit streams. So for this idea to have traction, in my mind, to continue to do research on it, we have to figure out how to build a complete computer that operates on stochastic bit streams. So a complete computer that has bit streams in, bit streams out. And in an ideal case, it would be a complete computer where the inputs, and the inputs to many types of computers are, let's say, analog values. So the inputs to the computer might be, if it's a microcontroller, it might be temperature measurement in the form of a voltage. We want to take those voltage values, which are the inputs, and convert them to stochastic bit streams right at the outset. We want those to be our inputs, and we want those bit streams to flow through the complete computer, doing whatever computation it has to do, right to the point where the output is, let's say, turn on the thermostat. That's a simple computer, but the complete computer. But it means that we have to do much more than just go from x to f of x. I think this is the solution. I think this is the solution because here, this hard thresholding allows us to do iterative computation. Any ideas why? So Jacob, why? This is an idea that's still percolating in my head, so it's an active area of research. But why could hard thresholding allow you to do because what I mean by iterative computation or a sequence of computations is you want a computer system that can process instructions, can do instruction, 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 instruction. Any ideas from anyone? So in a computer system, there's the notion of a program counter. So someone tell us what a program counter is. Hassan, what's Rishab?
Yeah, it's a value which stores the next address that the computer is.
Perfect. So it stores the address of the next instruction. So you want to go through a sequence of instructions, and it tells you where that next instruction is. And the program counter is something which typically gets incremented by 1. So go to the next, go to the next, go to the next. Your computer goes next, 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 next. Sometimes the result of a computation is don't go to the next instruction, but go somewhere else. That's a jump or a branch. But that's how computers are built. So here, well, if you think of it, the go to the next iteration of the program counter is exactly the sort of sequential operation that a finite state machine does. So the finite state machine is a machine, the entire computation is given the current input and given where you're at, decide where you go next. So imagine that the result of the computation was either 0 or 1. And it was the hard thresholding. So if you're slightly less than 0.5, it's 0. If you're slightly more than 0.5, it's 1. That could be the decision to either increment your program counter by 1 or to do something else to your program counter. So that's the hard thresholding that we would need. So the ideas are percolating in my mind a little bit more precisely than that, but I think I'd have to organize them before I discuss it. But all of this to say, I'd be real interested if anybody would want to think about this. How, as a research topic, think of a general finite state machine. So a general finite state machine would be one where we would have some sequence of states. They wouldn't all be laid out perhaps in this very regular structure, an irregular structure. How could you implement that type of computation in terms of bit streams in and bit streams out? But the complicated part is that here, if you think of it, the bit stream, which is the sequence of zeros and ones that's sputtering along, 0, 1, 0, 1, 0, 0, 1, that's kind of like the fine-grained computation. The fine-grained meaning that's the computation that's occurring in tiny slices. But the value that you're operating on conceptually is not an individual 0 or 1, but it's the probability that a sequence of those represents. So the state transition that you need is a state transition that's on not the individual zeros and ones, but that's on the value that they represent. So that seems like it's much weaker or much slower, and it is. But instead of just a 0 or a 1 value, now you've got a probability, which is a real value. So your finite state machine doesn't have to have input, doesn't have to have transitions that are triggered just by 0 and 1. It can have transitions that are triggered by real values. So if you have a quarter versus 3/4 or 5/8, 6/8, you can do anything. You can do different things based upon those values. And I think the key to make it a finite state machine at all will be the thresholding. You know, you do have to decide upon some number of values for which you do different things. Anyways, I'll see how it goes. But for the homework, I'd like to pose some challenges in terms of building such finite state machines. And for the non-computer engineers in the audience, this first homework may be the most challenging one because there's just a lot of circuit level stuff here. But I'll try to formulate it so that everything can be understood in terms of probabilities, for instance.
I want to talk about the random generator. if it represents a result value by binary representation, we can do a sequence of and use it to generate it. Because you only need 1 and 0 after you input the 1 and 0 into your organ, you have 12.5. And then you can easily get 0.2.
Okay. So, but with OR gates, in essence, the computation that you do